We've seen that the full Schrödinger equation for the harmonic oscillator contains a lot of constants like the reduced mass mu and the oscillator frequency omega that make the equations look a little bit more complicated than they need to look. What I want to explore in this video is to see how we can simplify some of those equations. This is the sort of approach that one might take when trying to solve a problem like the harmonic oscillator, and I'm providing this mostly as a means of demonstrating to you some of the tricks that you can use to make some of your mathematics problems a little bit simpler. Now, the whole idea here is we're going to try and simplify our problem by scaling the coordinate using an appropriate parameter. So I'm going to say that my new coordinate q is going to be some parameter alpha times my old coordinate x. So in other words, x is going to be equal to my new coordinate divided by this scaling parameter alpha, and d dx would be equal to alpha times the derivative of d dq. All right, so this is how I can go about substituting this. So my Hamiltonian for the harmonic oscillator would be simply minus h bar squared to mu d squared dx squared plus 1/2 mu omega squared x squared. And this is the operator that would be operating on the wave function to give me the eigenvalue equation. Now, if I want to convert these things to q's, I've got to do the following. Okay, this thing here is going to be equal to alpha squared d squared dq squared. And this thing here will be simply q squared over alpha squared. So my new Hamiltonian, in terms of q, would look something like this. It'd be minus h bar squared over 2 mu times alpha squared, the second derivative with respect to q, plus 1/2 mu omega squared over alpha squared times q squared. So now what I want to do is I want to simplify this Hamiltonian and make it so that each of these two factors are basically the same factor. In other words, there'll just be a multiplicative factor in front of a much simpler looking differential equation, and that different factor should be a factor that will essentially scale the energy levels as I go through. Let me show what I mean by this. If I want these two to be the same, then that means essentially that I want this factor to equal this factor. So I need to solve for alpha that does this. So let's collect all of the alphas on one side of the equation and all the other stuff on the other side of the equation. So when I multiply this alpha times this, I'll get alpha to the fourth. And then I'll lose these factors of 1/2. And so if I take this and put it on the other side, I've got to divide by this or multiply by mu over h bar squared. So I'll have mu omega squared multiplying by mu over h bar squared. So I'll end up with mu squared omega squared over h bar squared. Well, that's convenient. All right, what that means then is that alpha squared is going to be mu omega over h bar, or alpha is equal to the square root of mu omega over h bar. Now this may look familiar. Remember when we wrote down the Eigen Functions for the harmonic oscillator, the Hermite polynomials were written as functions not of x, but of x times the square root of mu omega over h bar. So in other words, there must be something to this if we're getting the same factor again when we perform this operation. Now finally, when I plug this value for alpha in, or for alpha squared, what is the common factor that these things get? So let me write that out. So I'll have negative h bar squared over 2 mu times alpha squared, that's mu omega over h bar, and this is times d squared dq squared. And then I'll have 1/2 mu omega squared over alpha squared, so divided by mu omega over h bar, and this is times q squared. So now when I work all this out, the mu's are going to cancel here. One of the factors of h bar cancels here, and I'll end up with negative 1/2 h bar omega d squared dq squared plus, and this is supposed to be the same, so let's check and make sure it comes out that way, and the h will now come up to the numerator, so I'll have 1/2 h bar omega q squared. Or another way I can write this is h bar omega times negative 1/2 d squared dq squared plus 1/2 q squared. All right, so you'll notice that this factor here actually also should look familiar, but this is the scaling factor. This has units of energy, and so this is the factor by which we're scaling the Hamiltonian. So we'll write a new Hamiltonian. I'll call that h dagger, or h accent, is equal to my old Hamiltonian divided by h bar omega. So in other words, this new Hamiltonian now has a very simple form. It's equal to minus 1/2 d squared dq squared plus 1/2 q squared. And so now this is the Hamiltonian, the effective Hamiltonian I need to solve. And you notice it doesn't include any of the parameters that are related to the harmonic oscillator. In fact, if I solve this, I'll get energy eigenvalues out that equal n plus 1/2. Okay, as they should be, because we're scaling the energies by h bar omega. So if I multiply this by h bar omega, I will get the energy levels for the full Hamiltonian. Similarly, when I write down my Eigen Functions in this new coordinate, I'll end up with the following. I'll have pi to the minus a fourth over the square root of 2 to the n factorial. So the normalization factor keeps all of that. I'll now have my Hermite polynomials, but they already have the weighting embedded in the coordinate, so I no longer have that added to it as I did in my earlier this expression up here. And then the exponential part is just e to the minus q squared over 2. So I hope you'll agree that this is a little bit simpler way of seeing those Hamiltonian and Eigen functions. And this is a little bit leads to a little bit simpler to solve differential equation. Now I want to take it a step farther, and in this I'm going to rewrite my reduced Hamiltonian here. Okay, so this is basically for a dimensionless harmonic oscillator somehow. A new aspect of this that I'd like to point out is that we effectively have P is equal to minus I ddq. Okay, it's in effect what we've done is set h bar equal to 1. So that means that the commutator of q and p is not I h bar, it's just equal to I. All right, so these things also are simpler in this new coordinate system. But what I want to do now is do something that's, I think, really fascinating, and it alludes to the algebraic operator approach to solving the Schrödinger equation for the harmonic oscillator. What I want to do is define a new operator, and this new operator I'll call A, and this new operator I'll write as 1 over the square root of 2 times the Q operator plus I times the P operator. Now if I plug in these expressions for this, that means that this operator can be written in effect like this. Okay, fairly simple looking operator. I also can talk about the complex conjugate of this operator as 1 over the square root of 2 q minus ip. And when I write that in terms of what it would be in this set, it'd be q plus q plus no I ddq. So now what happens if I take this operator and the A operator and apply them consecutively? I'll have two factors of 1 over the square root of 2, so I can just write that as 1/2. And then I'll have q minus minus d dq, sorry about the mess, q plus d dq. And we have to imagine if you will, that this is being applied to a function of q. So I'll have 1/2, okay, q times q gives me q squared. Q, then operating the differential on f, would give me q times the differential operating on f, minus d dq times q times f, which is going to give me a factor of q times df dq, but also it will give me a factor of taking this derivative just with respect to q and leaving the f, so I have to write that as a 1. And then finally, 2 successive operations of the differential operator, which gives me d squared dq squared. Okay, so reminder, this comes from taking d dq of q times f, and the derivative is taken with respect to the first factor of q, not to the f, so this just gives me an f. All right, these two terms cancel one another. So I'll end up with this thing being equal to 1/2 q squared minus 1/2 the second derivative with respect to q minus 1/2, the minus 1/2 being this term. Okay, well this is just this up here. This is just h dagger. So in other words, this combination of these new operators gives me my Hamiltonian minus 1/2. Or I guess another way to write this is that this Hamiltonian can be written as a dagger a plus 1/2. Now this may not look like much, but this is a key to getting ourselves into an operator algebra approach to solving the harmonic oscillator. Because with a few operator manipulations, one can show that the eigenvalues of this operator, which is also Hermitian, these have eigenvalues that are just the integers. So you can see that the eigenvalues of the Hamiltonian then must be equivalent to the integers plus 1/2. And this then, when we undo the scaling of the energy, ultimately leads us to the energy levels of the harmonic oscillator. All right, so once again, we see that using this operator algebra approach actually gives us a way to get the answers to the harmonic oscillator, and in fact it doesn't involve solving any differential equations at all. If we want to get the Eigen Functions out of it, then we have to solve a first order differential equation. But the operator algebra technique itself gives us the eigenvalues without ever solving a differential equation. So it's one reason why I think this is a fairly interesting and efficient way to look at the harmonic oscillator, but I apologize if the use of operator algebra is a little bit, shall we say, beyond the level of math that you might have seen before.